Hello, everyone. Welcome to the next episode of Meet the Young Professionals. Let me go ahead and share my screen again. So today we welcome you all in our today's episode of the Meet the Young Professionals, which would encompass a talk from Dr. Syed Shakib Sarwar, and he will be talking about embedded vision systems challenges in augmented reality or virtual reality. As you probably know that Dr. Shakib joined Facebook as a research scientist in May 2019. So as a part of the Meet the YP series, we want to invite the young graduates who were once a part of the IEEE Bangladesh section and who has now moved into different big companies and working in their problems and applying their skills to solve research problems there. So Dr. Hassan received his BSc and MSc in Electrical and Electronic Engineering from Bangladesh University of Engineering and Technology in 2012 and 2014. Then he moved to the United States and completed his PhD in Electrical and Computer Engineering from Purdue University, West Lafayette, Indiana in 2019. So his research interests include deep learning, system on chip design, VLSI circuit design, and neuromorphic computing. So today we would listen from him regarding his work on embedded vision system challenges and what kind of career opportunities that might present to our young professionals. So without further ado, I would like to invite Dr. Hassan to share his screen and give his talk.
Hello, everyone. Good evening. Thank you all for tuning in today for watching my talk. I'd like to thank Dr. Sajid for introducing me. I'd also like to add a few more things. My first profession was in academia. After graduating from BUET, I worked in BRAC University, Bangladesh for more than 2 years as a lecturer in the Department of IEEE. It was a very nice experience for me. Today, this time, during this time in BRAC University, I also did my master's in BUET. Then I came to USA for my PhD. In my third year of PhD, I did an internship in Facebook. That was also a great experience. I liked it so much that after completing my PhD, I joined the same team as a full-time employee. Before starting my talk, I'll quickly cover my research background. In BUET, I worked with Professor ABM Harunur Rashid for my bachelor's and master's thesis. I don't know if he's watching this talk. I'd like to express my gratitude for the opportunity and for the awesome experience of working with him. We worked on non-volatile random access memory design. We used memristors as the non-volatile element. We designed a 3-transistor 2-memristor non-volatile random access memory bit cell to replace the traditional SRAM bit cells. Our undergrad research was later published in IEEE Access. In my master's, I improved the design by reducing 1 transistor from the core bit cell. This made the NVRAM much smaller and low power compared to previous design and comparable with SRAMs. I started my PhD in Purdue University under the supervision of Professor Kaushik Roy in 2015. Initially, we focused on designing approximate compute elements for applications which can tolerate some degree of error. I designed a multiplication and accumulation unit which was low power, low latency, and small form factor compared to standard Mac units. However, our map provided incorrect results for few specific input configurations. To ensure that we can use this slightly faulty compute unit, we needed to modify the workload algorithm. The workloads we used were machine learning workloads, since they're error resilient. For this reason, we turned our focus to deep neural network-based algorithms and hardware. Our goal was to explore ways to improve energy efficiency of hardware and algorithms for deep learning. And luckily, this turned out to be one of the most researched topic in current industry. Currently, I work in the Sensors and Systems team in Facebook Reality Labs research, or in short, FRL research. There is some distinctions between FRL and FRL research. FRL, or Facebook Reality Labs, is mainly the product side, while FRL research is focused on research and development of next generation products. In consumer industry, our products are known as by the brand Oculus. Facebook's work in augmented and virtual reality spans a number of breakthrough technologies and touches industries ranging from entertainment and gaming to education and beyond. Oculus lets people defy distance with cutting-edge virtual reality hardware. In 2019, we released our most popular product so far, named Oculus Quest. It was completely wireless, which gave the users true freedom in virtual reality environment. We also had a more powerful VR product named Oculus Rift S. However, it was wired and required a powerful PC for the compute horsepower. This year, we released a more improved and advanced version of Quest as Oculus Quest 2. Needless to say that these amazing products are changing the VR industry very rapidly. In FRL research, our research teams invent and iterate on novel technologies that break exciting new grounds. And through it all, we have drawn inspiration from the legacies of Bell Labs and Xerox PARC as groundbreaking models of Center for Innovation. To improve our products, we have to work on many different exciting fields such as optics and displays, graphics, eye tracking, audio, interaction, ergonomics, computer vision, and so on. Each of these topics has incredible challenges and at the same time brings in so much excitement to our work. If anyone is interested to know more about these topics, I encourage you to watch the Connect videos, especially the parts by our chief scientist, Michael Airbrish. While improving the VR technology, Facebook is also working on augmented reality. Last year, in Oculus Connect 6, our developer conference, it was announced that Facebook is building AR glasses. We have all seen AR in science fiction and spy movies like Mission Impossible. But it is hard to imagine today in our hands. So, how AR glasses can change our lives? The first great wave of human-oriented computing started with the invention of computers, and its effect grew sharply with personal computers. However, the effect is almost at saturation, as personal computers are slowly getting replaced by handheld devices like phones. According to our chief scientist, Michael Airbrish, The second great wave is starting with the advent of ARVR, and we should see the sharp growth when AR glasses will be at consumers' hands. AR glasses promises to give superpowers to humans. However, the challenges to this path are formidable. The glasses have to be lightweight so that we can comfortably wear on our faces. It has to consume minimal power to ensure all-day usability. At the same time, it has to be in a form factor that is socially acceptable. To enable main features of AR glasses, machine perception is an important feature. Using machine perception, we can design a personalized and contextualized AI assistant. However, to have this human-centered technology, we need egocentric data, which does not exist yet. To bootstrap this research effort, Facebook announced Project Aria. It is designed to record high-quality egocentric data, which enable researchers to design state-of-the-art machine perception-based AI. This is a research tool and not for sale. Today, I'll not discuss the details of Project Aria. Rather, I'll talk about some features of this tool, which will give us some idea about the key challenges of embedded vision systems. Let's consider the input modalities of this tool. It will have a megapixel RGB camera for capturing data for AI and semantic understanding. It will also have mono VGA cameras for tracking head, hand, and object movements. In addition, it will contain non-visual sensors like IMU, magnetometer, barometer, and GPS to enable non-visual tracking. All this requires cutting-edge technology, even just to record data without doing any processing. Note that this device does not have a display. The sole purpose of this device is to only record egocentric data for research. I hope you got some idea how much complicated it is to combine all these technologies in the small form factor with significant power constraints. Now let's come back to the challenges of embedded vision systems in AR/VR. In this talk, I'll focus mostly on the vision or image sensors. The sensing technology enables a lot of AR/VR use cases. First, I'll briefly walk through different properties of those sensors. The cameras are for mainly machine consumption and not for taking nice pictures. Hence, a low-resolution monochrome camera may be good enough compared to power-consuming megapixel cameras. On the other hand, we need all the information we can get from the scene at a very high frequency. This means our sensors have to be always on. So, preferable features of the sensors are global shutter, low light sensitivity, high dynamic range, and high frame rates. The global shutter sensor can capture the whole frame instantaneously, which is beneficial since AR/VR use cases contain a lot of head motions, and the cameras used for tracking are on the head-mounted devices or headsets. The low light sensitivity allows the user to use the device in challenging lighting conditions. Similarly, for many important computer vision use cases, it is vital to have high dynamic range sensors. Last but not the least, frame rate is very important for continuous tracking. A few years ago, we used to use DSLR cameras for getting high quality pictures with all these features. Nowadays, our phones can do most of that. However, a major part of it is computational imaging, which requires significant post-processing. Yes, the phone can do that automatically, but it consumes significant amount of power. And you cannot do that for, in an always on use space due to thermal and power constraints. To ensure the satisfiable sensor characteristics, we need to also consider other behind the scene issues such as memory requirement for the captured pixels and non-idealities on the sensing device. The captured pixels are needed to be stored or buffered before they can be shipped for processing and consumption. Hence, the larger the image resolution, the higher on-sensor memory is required for the global shutter digital pixel sensor. The sensor can have various non-idealities such as defective pixels, fixed pattern noise, etc. These issues are usually taken care of by the ISP or image signal processor before the data leave the sensor. In summary here, I like to say that the sensor hardware is an important part of the computer vision stack that enables machine perception-based use cases. And any compromise we make at the hardware level should be tolerable at the end-to-end device use cases. Now, moving on to the application domain of embedded computer vision system. We need to solve positional tracking in ARVR. It enables the world logged contents that you go through in virtual and augmented reality. So it's not only 3 degrees of freedom, which tells your head orientation, but also where exactly your head is in the room. That is 6 degrees of freedom pose. On top of that, you need one or more input interfaces. Recently, we enabled hand tracking that allows users to provide input using only their hands, no controller required. Hands don't have IMUs or accelerometers. So this is a pure computer vision problem. Now, the goal for AR is to overlap virtual objects with real objects. So ideally, you should also be able to localize and segment every single object in the field of view. Finally, eye input is extremely important for a bunch of reasons. I won't be able to go into the details, but in a nutshell, eye tracking is a go or no-go case for advanced ARVR. All these problems are quite machine learning focused. A typical classification or segmentation network could achieve most of these tasks. For example, a model can be trained to find the bounding boxes of a hand. We also need to localize the object in the scene to enable occlusion in order to render an object in front of or behind the real object. And that is still a difficult problem, locating everything in the scene. Another approach would be to segment the scene for different occlusion planes, which is essentially depth. It uses 3D point cloud type of data as model inputs. The list of such applications could go on and on. In summary, the basic workloads are detection, segmentation, classification, tracking, etc. These tasks can be carried out via deep learning, which is the most popular nowadays. However, few tasks are still more accurate or efficient, or both, using traditional machine learning and computer vision. For some cases, a hybrid approach is taken by combining all these methods. Finally, I'll discuss the necessity of machine learning optimization and several off-the-shelf methods. As I mentioned, the deep learning methods are currently most used for solving tracking problems. However, the deep neural networks are compute and memory intensive. They're also not suited for general purpose computing solutions. Almost all state-of-the-art deep learning algorithms are developed using large amount of data and high performance computing. The high performance computing is mainly leveraging parallel processing power of GPUs. However, for practical use cases, we cannot use GPUs as they are not small enough to carry all the time, and also requires great amount of power and generates significant amount of heat. For efficiently implementing these complex neural networks on mobile hardware, the researchers have come up with various methods and tricks over the last decade. To mention a few, I can say efficient memory hierarchy, coefficient and activation pruning, feature map compression, layer fusing, etc. These are the main contributors in optimizing machine learning algorithms. In comparison with the algorithm designers, we are interested not only in accuracy, but also in other metrics like accuracy per bit of input data, accuracy per joule of energy consumption, and accuracy per latency. One important thing to note here is that not all these optimizations translate well into hardware implementation. For example, in theory, depth-wise separable convolutions are orders of magnitude more efficient than regular convolution. However, they are not that efficient when used in hardware accelerators, since the memory pattern or data flow is not favorable. That essentially means only algorithm improvement cannot provide us the solution in the silver platter. We need to co-design the hardware as well to benefit from the algorithm improvements. This is a relatively new field and has a lot of promises. With all these challenges and promises, I'd like to end my talk here. I want to thank Facebook for giving me the opportunity to work on these exciting topics and allowing me to share the issues of it with you. I also want to acknowledge my team and the management for contributing on the things I have shared today. Finally, I want to thank IEEE Young Professionals community for hosting me today. Thank you all.
Thank you very much, Shakib, for the excellent presentation. And I think you summarized very well how your company's particular division works in terms of developing new product and what are the challenges. Now the floor is open for questions. So we would like to take some comments or questions from the audience. So I think Nazmul Haq Turjo has a question. So since we don't have a lot of participants in the audience, I would like to invite Nazmul Haq to unmute and ask the question himself.
Thank you, sir, for your talk. My question is, we all know that for deep learning, GPU architecture is the best. But my question is how embedded system architecture works like a GPU architecture.
So if I understand correctly, you are asking that how embedded system can work as a GPU architecture, right?
Yes.
Okay. Yeah. So in embedded systems, usually for deep learning use cases, separate hardware accelerator is used, and that is somewhat similar how the GPUs are optimized, but they are more specific to the workload. For example, most of the state-of-the-art embedded hardware accelerators focus on optimizing the convolution operation for deep learning networks, whereas the GPU is mostly general purpose graphical processing unit. It's not that optimized compared to the embedded hardwares. On the other side, there are several constraints on embedded hardware accelerators like power, latency, and form factor. In embedded hardware, you cannot have that much area for having SRAMs. So all these things make embedded hardware different from GPUs. But the main goal is the same, to accelerate the workloads.
Thank you.
Did I answer your question?
Yes. Thank you.
Thank you.
All right. Thank you very much. Is there any other questions or comments if anyone wants to add anything? If not, while you think about the questions, I would like to quickly share my screen for a while. Let me go ahead. So this is a virtual certificate of appreciation. We usually present it to all our Meet the Young Professional series webinar speakers. So it's gratefully acknowledged today that Dr. Shakib Sarwar was a speaker at our Young Professional event, and he took the time to prepare this wonderful presentation for us and discuss all the topics regarding his current work and the challenges. So this certificate is presented to him as a virtual token of appreciation on behalf of the IEEE Young Professionals Bangladesh.
Thank you very much, Dr. Sajid and IEEE Young Professionals. I'm truly honored and happy to receive this. At the same time, I'm really happy for getting this opportunity. Thank you again.
Thank you. So if there is any last moment questions or comments, if anyone wants to add anything, or otherwise we can thank the speaker once again for giving the wonderful talk and conclude today's session. Thank you very much, everyone.